Good morning and welcome to today's crop hour. This is the last day of our corn week, and we are excited to see you join our session. Just a little bit of housekeeping. If you have any questions or comments that you'd like to make throughout today's webinar, please utilize the chat or the Q&A feature, and we'd be happy to get those questions addressed. You know, for those that are looking for CCA credits, I'll have one QR code that I'll show at the end of today's presentation. And so our first speaker will go through two different topics, but we'll go through one, take a quick 3-poll question or survey, and then he'll launch into, take any other questions, and then he'll launch into his other topic where we'll do that same 3-question poll, and then we'll end with that QR code at the end of today's session. And so again, if you have any questions, please feel free to put them in the chat or Q&A. My name is Connie Strunk, and I'll be your host and facilitator today. So with that, I'd like to introduce our first and only speaker today is Dr. Jason Clark. He's our soils specialist with SDSU Extension. So Dr. Clark, if you would be so kind as to share your screen and go ahead and get started.
All right, so for today's webinar, we're going to cover a couple different topics, all revolving around corn. The first one, we're going to hit on phosphorus, potassium, and then we're going to take a little break, and then we're going to go through nitrogen. And just as a quick reminder, for a lot of these research presentations, things like that, if you want us to go back and see them, I think they'll put them up on the extension website. But if you go here to this SD State Soil Fertility YouTube page, you can see also this will come up right here, and we have the videos for nitrogen rates and corn recommendations, as well as some of the phosphorus and potassium stuff isn't up here yet, but all the nitrogen stuff is, and the phosphorus and potassium will be up in the next little bit. Also a little bit about nitrogen fertilizer testing, some products. This is one location you can go, just SD State Soil Fertility right here on the YouTube, and kind of get some of these presentations as well. So that's where you can see some of that. We also post updates on other social media to kind of direct people. But to get started on today's phosphorus and potassium part of the project, we'll go here. And usually what we start with when we're talking about P and K is we'll get our soil test report out right here. We will go to our phosphorus and potassium and kind of see what levels they're at. And from there, we will make a recommendation for how many pounds per acre of those fertilizers that we want to put on our farm, on the different fields or zones in our fields. And for just some context, the results from what we'll be talking about today, these are all based on South Dakota data. You can see here in the starred areas, these are where the different fields were across central and eastern South Dakota. So we have a good number, 35, plus we have about 7 more from 2022. So around 40 different sites that this information is coming from. So first of all, we're going to hit on phosphorus. So with phosphorus, we talk a lot about a critical value, and what that value is relating to is this relationship right here, where we have a yield or relative yield, a percentage of yield, and then we have a soil test level starting from 0 and going up to, whatever that is. And as we see here, we see yield increasing until a certain point at that soil test level, and then we see it tend to flatten out where we no longer see a response to fertilizer application. And for phosphorus, that critical level is at 16 parts per million for the Olsen test and 21 parts per million for the Bray test. And this is really important to recognize what soil test value you're getting back from your soil lab. So Olsen is really good for higher pH soils above 7.4, and Bray works for soils that are less than 7.4. Olsen works for all soil test levels. We don't have one for Malic, so you want to make sure when you're doing your soil test levels, make sure they're not testing for Malic. There is a conversion, but it's not as accurate as just doing the Olsen or the Bray test. So when you are getting your soil test results, make sure you're understanding whether it's an Olsen value or a Bray value. So we see this relationship right here, and what we want to do is see what that's actually like in the field from field research data. So on this graph here, we have our relative yield across those 35 to 40 sites. And we have our Olsen P level right here. And what we want to see that relationship. So anything below 100%, this line right here, we'd say is responsive to fertilizer application, because without it, we didn't see we saw a lesser yield. And when we're above 100%, around 100% is usually where we don't see any more increases in yield. So if we look at the dots right here, you can kind of see that there tends to be a relationship. When we're lower here, we see a response over below 100%. And then as we get over here, we tend to be up and down around 100%, which is what we're looking for. So there's a few ways we can do this. I just want to show you several ways that we can kind of put a model through this. This one's called a quadratic plateau. It's just a quadratic line until it hits a flat point. And that line is around where it levels off is around 20. If I use a linear relationship through here and then plateau, kind of go flat right there, it's about 16. If we use what's called a Kate Nelson, which is what my predecessor used, so the previous value of 16 is based on this test right here. It still says it's right there around 16. And then if we take the average of these different models, just because they all have their disadvantages and advantages, and kind of just take an average, it's around 17 parts per million. So not a lot different from what we've seen in the past, where, past research before 2018, when I started doing this, it was showing 16 was still accurate. And this is showing 16 still pretty close. And we might be able to up it a little bit more, but not a whole lot. These lines right here just represent confidence around this point of how accurate we think we are. And we'll go over those numbers in this next table right here. So we have those critical values based on the different models. And I just to kind of show you some different numbers here. And they're between 16 and 20. That average is 17. So pretty close to the 16 that we're at. If we want to see the confidence around that point, so if you were to draw multiple lines through there using these different techniques that we have, just to kind of get, is 16, the drop dead, or is there a range that we're looking at here? And if we look at that range, for linear, we're 12 and 19. Quadratic is usually a little higher, that's 16, 26. One of the disadvantages of this one is it does tend to be a little bit farther to the right, higher numbers, which is not as accurate, in my opinion. It's a little bit more of the middle ground between these two. Kate Nelson between 11 and 20. If you take that, this is probably the most accurate thing, is to take the advantages and disadvantages of each of those and say, if my soil test is between 13 and 22, I have a fairly low likelihood that I'm going to see a response to phosphorus. And that's kind of a good range we probably want to aim for getting our soil test levels to, and that 17 being in that middle. So if you're between 13, 17 is kind of on the lower end, but if you're between 17 and 22, that's a really high chance you're not going to see a fertilizer response. So that's one way to look at phosphorus fertilization and seeing how it impacts what we're doing. Another way that I think is pretty interesting is to look at that change in yield. So that's what we'll look at here. So when we add phosphorus fertilizer, how does that affect my yield? Do I get an increase in bushels, a decrease in bushels? Does it stay the same? So that's what this is right here, average change in yield. If we hit for at 0, that means we had no change in yield from adding phosphorus. If we're above it, that means we had an increase in yield. Below it, we had a decrease in yield. So this is a relationship that we saw there. So we can see, and this makes sense, at low soil test levels, we saw the biggest change in yield, about 15 bushel per acre. Yield going down as we increase in soil test value until we hit a 0 right here on this line. And that value is around 22 parts per million. But a lot of times when I've asked farmers, so how much change in yield do you want to see before you're going to do something out in the field? And a lot of them say 5 bushels per acre. So if we take over here and we say, we want this 5 bushel per acre increase before I'm going to go through the effort of adding phosphorus. So if we do that, run over to the line here and run down, it's right at that 16 parts per million. So once we hit that 16 parts per million or less, that's usually when we're going to start to see a bushel increase. And that's where our recommendations start asking us to recommending to add fertilizer is below 16 and below. So that still seems fairly accurate. Another kind of way to look at that. The third way and final way we're going to look at this phosphorus response is how frequently we respond to phosphorus. So if we responded an increase of 5% or more, we say, yes, you responded. If it's decreased in yield, which will actually show some data that we can see some reductions in yield when we add phosphorus, we'll see that relationship here. So again, soil test level down here, we look at the percentage of time where we saw a yield increase. the relationship looks like this, which is what we'd expect. If we're at a lower soil test level, we're going to see a higher chance of phosphorus response. As we increase in soil test level, we see a decrease in response. Now this next line, the blue line, is going to be our chance of seeing a decrease in yield of 5% or more. So you can see as we increase in soil test level, we tend to see an increase in the chance we're actually going to see a reduction of 5% or more in yield, which usually when we think of adding phosphorus, we just think it's adding money in the bank, but at times we can add too much where it's going to, for whatever reason, whether it's too many salts or other things like that in the soil, we're actually going to see a decrease in yield. And this yellow line is just the percentage of the chance where it doesn't do anything. It just remains constant. And it's that same relationship. But where these lines potentially go down and they meet, where we have an equal chance of increasing or decreasing yields around 20 parts per million. So we can see that 16 to 20 range down in here is usually at critical value, is usually where we're seeing, little to no changes right in there. Confidence around that, 13 to 22 that we were talking about earlier is likely where we want to keep. Anything above that, probably not worth it economically. And even in there, that 16 to 20 is probably a good cutoff range to use of needing more, just putting on maintenance. We want to see that 5 bushel per acre increase. That's at 16 and less. So we did, if we remember that graph, we did see a good amount of scatter in it. So one thing we've been doing is, if we want to just see the accuracy of just using soil test phosphorus by itself to say yes or no to increasing yield, we're about 68% of the time we're correct, whether we say we should or should not apply. So the other question that we've been looking at is what else can we add to the equation or to our decision-making process of whether we should apply phosphorus fertilizer? Because we've seen if we have too high of a soil test level, we might see a decrease in yield. However, sometimes we have higher soil test levels, but we still see a response. So what else can we use to help us make that decision? And this is still data I still need to work on, but I just want to show you that some of the basic results in the end, that if we use that Olson's phosphorus test plus the soil respiration, which is basically measuring kind of the amount of respiration, the breathing of those microbes. If we use that plus your cation exchange capacity and your clay content, we can go from 68% right here to 74% accuracy. So we're increasing it by about 6%. It is better. It's still got some testing to do to see if these are the ones we want to use or if there's some other ones, because we know phosphorus and biology kind of go together. So can there be some other measurements to help improve this? And we have some ongoing research the next few years to help us with some of this as well. So that's phosphorus. We're going to move really quickly here to potassium. Similar type of studies we're looking at these together. If we look at that yield versus soil test level here, the traditional value that we've used is 160 parts per million. Of that cutoff value, anything less than that, we say fertilize. Anything more than that, we say likely won't respond. So we look at the data for this. And we look at that relative yield. Potassium's a little bit more difficult to work with. We'll just say that. We don't have as many lower soil test levels because the soils in South Dakota are just naturally abundant. So it's harder to get the area down here to see what that yield would be. So we don't have as much room here to work, but we can see generally we're below 100% about right here. And somewhere around here, we hit pretty consistently. We're up and down around 100%, which is not likely to increase yield. So we can draw a few different models there. This quadratic plateau we talked about earlier tends to be a little bit far on the right. And you can see this about 240, which I would say is a little high. If we take off a percentage or two of what we want to hit, we're close over here to about 190. And I'll show you that in the table in a minute. It's probably a little bit more accurate because we don't change much between here and here, but that's a big increase in soil test level. As well as that linear model is showing us about 198. The Kate Nelson, which is what we've traditionally used, is about 175, which is still higher than the current 160. If you take the average of them, we're looking at this purple line right here, which is about 207. So it shows us we might need to increase. We do have about 7 more sites that need to go into this data set from 2022 to see where that data takes us as far as the accuracy of this. So nothing official here. This is about 40 sites, but we have about 5 or 6 more that will go in here to look at these numbers. So we might need to increase the soil test values some with this data, but this is some preliminary data we still need to work on a little bit. These are just the ranges that we're seeing the confidence around. You can see around these levels right here, is where we're looking at, and we'll look at the numbers here in a second. So that linear, that value is 198. Using that quadratic is 247, and it's red for a reason. We'll talk about that here. And so it's 247. If we just, instead of going for 100% of what that model says, if we just go for 99, we see that drops from a critical value of 247 to 208, which is, 39 parts per million different, which is a good chunk, and it shows you how slowly that line goes up and just takes a while before it stops going up anymore. And the interesting thing, if we take off 2% of it, from there we go down to 190, and you can see we have just in a change of 1%, we drop 39, then we only drop 18. So it shows us between here and the -1 and -2% from the full model, we're closer to that responsive part, which is where we want to be. If we look at the Kate Nelson, which is what's been traditionally used in the past, and that's how 160 was established, it's at 175 here, which shows us it might need to increase some. If we take that average, if we include the 247, the average is 207. If we don't, it's 190, which I think is probably a little bit more accurate. And these are just the confidence areas, 175 to 220, 150 to 190. Those are probably 150 to 190 is probably a good range of where we want to maintain our soil test levels, just to for sure maximize those soil test K levels, whatnot there. And these are kind of the averages that I would go by instead of using this model here. But I just want to show you this is what we're looking at and questions we need to make sure when we're looking at other people's data. Depending on what model they use, the data might give you a different answer. So it's really important to know what's been done in the past and the pluses and minuses of them. But usually the advantages and disadvantages, if you average those together, I think those are the most accurate numbers to use. And that's what you're seeing here in the that's circled here. So the interesting about potassium, if we remember, the phosphorus had this really cool relationship when this change of yield, it went down and flattened out. Potassium, not so much. You can see, this is a 0 line and we're just scattered around 0. Look at these soil test K levels, decreasing in yield if we add too much. So again, this is showing us if we have high soil test levels and we add more potassium, we can reduce yield. So this way of looking at it hasn't worked very well for our South Dakota data and potassium, but it did for phosphorus. We're looking at this response frequency. Interesting thing here, if we just look at how if we can actually lower yield, and we can see as we increase in soil test K, we can lower yield by adding K, but also, most importantly is we have a chance of increasing it or just maintaining it. And right where those kind of split is that 120 range. So it's a little lower than the traditional 160, but potassium data tends to be a little more messy. And that's why we're trying to look at mineralogy and clay types and other things to help us improve that. So if we look at the summary there, if we're trying to maintain, our data shows that if we're trying to maintain our critical values between that, that 175 to 198, that critical range 165 to 205, this one's probably about the range where we want to keep our soils to make sure we're optimizing our yield. That 5% or 5 bushel per acre increase, we didn't have a good relationship, so we can't really use that there. If we use soil test K by itself, we're at 63% accurate. And so the other question was we're looking at is what about other soil tests there? And what we found is if pH, soil test K along with pH and tillage, we can up it to about 77% accurate. So it's showing us that our potassium is interacting with tillage and also pH, and this is no-till versus conventional. And that with using those different ones, we can also do it. The thing that's not in this data set that will be in the next 6 months is my graduate student work on the data is clay mineralogy has shown to be pretty important up in North Dakota, and Minnesota has shown it some as well. And we're looking at how the mineralogy in our clay types of how well they hold on to K or release K can also help us improve our K recommendations. So that's something that'll hopefully go into this and hopefully increase the 77% up quite a bit more than what it is here to a little bit better accuracy. But that's something that'll probably come in next year's crop hour and this summer. So that is kind of our phosphorus and potassium update.